Okay, this is the video solutions to Unit Test 6, and Unit Test 6 introduced the concept of exponents and solving by common base or by log method. And so going to start here with this first question. 32 to the x power equals 8, and 32 to the x power equals 8. You think about exponentially what's going on. Think about powers, and of course 8 is 2 to the third, and 32 happens to be 2 to the fifth power, and that of course is being raised to the x power. And now when you raise a power to a power right here, this is going to be 2 to the 5x, okay, equals 2 to the third. And now since the expressions as wholes are equal, right? And since we have the same base, that's what we mean by a common base, then we know that 5x would have to equal 3. And so x would equal 3 fifths. Okay, so there's your answer for question 1. Question number 2, we have 3 to the x minus 1 equals 1 over 9. And so thinking exponentially, of course, we have a base of 3, and then we have this 1/9 over here. First change I'll make is I'm going to rewrite the 9 as 1 over 3 squared. Right? And then I'm going to use what we call or refer to as the 1 over rule. The 1 over rule says if you have x to the negative a power, uh, you can reverse the sign of that exponent from a negative to a positive by merely moving that any multiplied term to the denominator. And of course, in that, you can run that the other way. And so in this case, what I'm going to want to do is move this 3 to the second power that's in a denominator. I'm going to move it to the numerator. All right. And you can do that by merely changing the sign of the exponent. So it becomes 1 times, and of course 1 is the multiplicative identity. So it's going to be 1 times 3 to the minus 2 power. And now I've obtained the common base of 3. And so x minus 1 has to equal negative 2. And if I add 1 to both sides using the basic elementary algebra additive inverse principle, we get x equals minus 1. And we have our answer. Okay. Um, question number 3 is a spiraled in question, and it's a factoring question to factor completely. And as you look at it, 4 terms, and the first two and the second two have some commonalities. And so we're going to use the factoring by grouping technique. And on the first pair, I'm going to factor out an x squared. I'm going to divide out an x squared from both of the first two terms. And that's going to leave me with an x, and of course a minus, and a 5. And then on the second two terms, they're both multiples of 4. And since this sign on this negative 4x is indeed negative, I'm going to factor out a minus 4. And so when you divide out that negative 4 from negative 4x, that's going to leave you with just a positive x. And the plus 20 divided by minus 4 is going to leave you with a minus 5. And now as you see the structure of this, we have something times x minus 5, and we have negative 4 times, again, x minus 5. So that element is common to both pieces of this expression. And so you're going to factor out the x minus 5 from each term. And when you do that, you're left with, from the first term, an x squared, right? When you factor out this x minus 5 right here, you can be left with just an x squared there. And from the second term, you're, of course, going to have a minus 4. And now that is factored, but it's not factored completely. And you should recognize the x squared minus 4 as a difference of squares. And so that can be factored into what we refer to as a conjugate pair. And so you'd factor that into an x plus 2 times an x minus 2. And so that's the answer we were looking for on that. That's completely factored now. And so factoring, of course, a big part of calculus, and sometimes we see a weakness there. So I'll get rid of these writings and then slide down the page and take a look at our next bunch. Um, right there, I guess. We have question 4 here. 4 to the x power equals 21. Now, in this case, again, a variable exponent. So this is what we mean by an exponential equation, an equation where the exponent is a variable. And a base of 4 and a base of 21. Now, in terms of uh, powers, of course, you could rewrite the 4 as 2 squared. But the 21 is not an integer power of 2, obviously. So instead, what I'm going to do is use a log technique, and I'm going to just log both sides. So I have the log of 4 to the x power equals, of course, the log of 21. And then right here, I'm going to use a log law that was identified as the log of a to the b power, and that's equivalent to b times the log of a. Now, the reason for that is when you raise a power to a power, you're allowed to multiply the powers, right? This log law comes from this rule. If you have x to the a to the b power, that's equivalent, right, to x to the a times b. And so that exponent law is where this log law comes from. And so now I'm just going to use that rule, and this x is now going to be multiplied times the log of 4. So I suppose the answer to how do you solve exponential equations is in some ways you don't. You turn them into multiplication problems. And then you simply solve, of course, by x times log 4. So you solve by division. Right? This is multiplied right here. So to solve that, we just divide by log 4. Okay? And so that gives us x equals log 21 divided by log 4. Okay. Another way you could write that, of course, this is written as a base 10 situation. This would be equivalent by something called the change of base formula that you should have had in Algebra 2 um, to the expression log base 4 of 21. So that's another way to think of x. And what that means is 4 to some power is 21. What you're thinking right here is you're thinking 4 to what power is 21, and that's what your x represents, right? So I know that 4 squared is 16, and I know that 4 cubed is 64. So this number, log base 4 of 21, or log 21 divided by log 4, this number has to be somewhere between 2 and 3, and much closer to 2. All right. So that's an example of an exponential equation where you can't obtain a common base. And so now I'll just get rid of this, and we can move on to our exercise number 5. And exercise 5 says 2 to the x power uh, times 8 to the x power equals 12. And of course, in terms of exponents here, if you realize that 8 can be written as 2 to the third, and then that is being raised to the x power equals 12, okay, then you can get directly to 2 to the x power times 2 to the 3x power equals 12, right? Raising a power to a power, you multiply the powers. And then from there, we'll go to 2 to what power? Well, what do you do when you multiply two terms with the same base? You add the exponents. So that's 2 to the 4x equals 12. And now at this point, it should become obvious, if not before, that 12 is not an integer power of 2. 2 cubed is 8, 2 to the fourth is 16. So we don't have a way to use the common base technique, and instead we'll use the technique we just used a moment ago in question 4. We'll go to the log situation, the log technique, and we have the log of 2 to the 4x equals the log of 12. And then I'll use the log rule that allows me to turn this into a multiplication exercise. So it becomes 4x log 2 equals log 12. And now we can divide. So what is x going to equal? When you move this multiplied 4, and when you move this log 2, you're going to have log 12 over 4 times log 2. And if you prefer, another way you could express this is 1/4 of the log of 12 divided by log 2. Could write it that way. I think most people entered it into the through the CalcPad this way, but this would be acceptable. And of course, you can also write it like this: um, 1/4 of log base 2 of 12. So a couple different ways you can write that expression. Uh, Probably put in this question number 6, which is a spiraled in question. It goes back to inequalities. And so I'll just get rid of this writing here and just slide down the page just a little bit. Move this up and look at the inequality that you're trying to solve. Quadratic inequality. X squared minus 3x plus 2 is strictly greater than 0. Now, the technique we've been using is to get rid of the inequality and treat it as if it's equality. So it's x squared minus 3x plus 2 equals 0. This will factor rather easily. It's going to be an x and an x. Both signs will be negative signs. And in some order, you're going to use a 1 and a 2. Out of that, we would know that x minus 1 equals 0, or x minus 2 equals 0. The idea being that if you're multiplying two numbers, and that's all these things are, and getting a 0, then one of them must be a 0. So one number I'm going to be concerned about is 1, and the other number I'm going to be concerned about is 2. Okay? Um, You would then go to a number line and perform a test on the intervals determined by your solutions that you arrive at through the equality. So one number I'm interested in is 1, and the other number I'm interested in is 2. And because this is a pure inequality, there's no line under here, right? There's no equal allowed. It's strictly greater than. Those circles are going to stay open. And then you would just test each of these intervals that these points suggest. So for instance, if I test the number 0, which would be to the left of 1, then pretty obviously we have x squared minus 3x plus 2, and the question is that greater than 0? Well, obviously x squared is a 0, minus 3x is a 0, and then we're adding 2. And so pretty obviously 2 is greater than 0. That's a yes condition. That's a true condition. So numbers in this interval will work. That would be part of our solution, right? So we'd shade that area. If you try a number bigger than 2, for instance, if we test 3, then we're going to have 3 squared minus 3 times 3 plus 2. And again, questioning, is that greater than 0? Testing to find out if that's greater than 0. Well, we've got 9 minus 9 plus 2, and we're asking, is that greater than 0? And so is 2 greater than 0? That's a yes. That's a true condition. And so numbers up there will indeed work. And that becomes part of our solution. Those numbers are acceptable. Okay? And finally, a number in between 1 and 2, if we were to test like x equals 1 and 5 tenths, then we'd have 1 and 5 tenths squared minus 3 times 1 and 5 tenths. And then we'd be adding 2, and the question is that greater than 0? Well, 1 and 5 tenths squared happens to be 2 and a quarter. And minus 3 times 1 and 5 tenths is minus 4 and a half. Minus 4 and 5 tenths. And we're adding 2. And the question is that greater than 0? Well, 2 and a quarter plus 2 is 4 and a quarter. And when you subtract 4 and a half, are you going to be greater than 0? Well, no, because you've got negative 1 half. And is that greater than 0? That's a no condition. So numbers in that interval don't work. Okay. Finally, what you need to do is to shade appropriately, uh, use the virtual tools, and hopefully you've become familiar with those. And all should be well with that question. All right, so that's questions 1 through 6 from Unit Test 6. Hope you found them helpful.